So it's the moment you've been waiting for. Why do we care? This question of octopus locomotion. So let's revisit the question. An octopus uses conservation of momentum, which is essentially jet propulsion, to move through the water. They do this by pushing water behind them using their tentacles. And since momentum must be conserved, they must be pushed forward in the process. So again, if the octopus is pushing water back, right, then in order for momentum to be conserved, the octopus must go forward. And this is intimately related to Newton's third law, because if the octopus pushes water back, the water needs to push back on him with a certain force, right, with an equal and opposite force. And that force ultimately is what accelerates the octopus. All right, so let's suppose the octopus is currently pushing 0.8 kilograms of water with every thrust at a speed of 2.1 meters per second, and that he is moving forward with a speed of 0.7 meters per second in the process. Okay, so just imagine you got this octopus at rest, and then it pushes water back at a speed of 2.1 meters per second, and he goes forward at 0.1 meters per second. Okay, the octopus sees a shark then and decides to skedaddle. Consequently, he pushes harder and drives a full kilogram of water at a speed of 3 meters per second. What would be the new speed of the octopus? Okay, so one thing might be glaringly obvious in this problem. So far, there's no mass, right? If we're going to solve this problem, we need to actually know how much mass this octopus has, right? So let's start out by using that first conservation of energy situation, right? So basically, if we'll start with P1 or P before equals P after, right? So if the octopus is at rest, his initial momentum is 0, like many of the problems we've done, okay? And after, right, he's pushing the water back at negative 2.1 meters per second, right? And the water has a mass of 0.8 kilograms, right? So that's what he's pushing back, right? But in the process, he's moving forward at a speed of 0.7 meters per second, right? And he has a certain mass. So basically, this part here is just the momentum of the water, negative, right? Plus the momentum of the octopus, right? And that all has to add up to 0. Okay? If I bring this to the other side, divide by 0.7, I find myself with a mass of 2.4 kilograms. Okay? So this little guy, this little octopus weighs 2.4 kilograms. Okay? But that's not what we're solving for. What we really want is, what is the speed of this octopus after he skedaddles, right? After he's trying to race away from this shark. And so I'm going to erase a little bit of this so that we can see the problem a little bit better. So I'll just break this up into a before and an after. So for this problem, the octopus is already going at what speed? Well, 0.7. So we have, I'm not sure how much that looks like an octopus. Kind of, I guess. Right, so this guy has a mass of 2.4 kilograms, right? And he's shooting away at 0.7 meters per second. So that's my before, right? And then he starts shooting away at a higher speed, which we're trying to find out. Okay? And he's pushed back all this water, right? A full kilogram of it at 3 meters per second. Okay, so let's do the conservation of momentum. We know that P1 equals P2, right? The momentum that the octopus has to begin with is 2.4 mass times 0.7 meters per second, right? That's the mass times the speed of the octopus in the positive x direction. And that's turning into a negative, well, a 1 kilogram times a negative 3 meters per second, right? He's pushing this water back, so that's a negative momentum. It's going in the negative x direction. Plus 2.4 is the mass times v2, right? The new speed of this octopus after he accelerates, okay? So if I multiply these two, multiply that, you just get -3. Add it to the other side, divide by 2.4. I get a v2 of 2.37 meters per second. And this is, as always, when we get an answer, a good time to ask ourselves, does this make sense? All right, well, should it be faster than the original speed? Yes, it should. He is pushing back all this extra water, which should cause him to actually have a higher speed. Is it astronomically higher? No, it's reasonably higher. And he's pushing quite a bit of water, 1 kilogram of water, at 3 meters per second. Right, so yeah, I'd say this is a good estimate, a good ballpark. And now, most importantly, you guys have a little bit of a better sense of how some creatures on the planet use the principles of physics, like momentum and conservation of momentum, in order to evade prey and to survive. It's pretty cool.